Welcome to your channel, Silent Mind Studio, and thank you for listening to us. Today, we're diving into a topic that's, well, literally out of this world: satellite internet. You've sent us a whole stack of fascinating sources, articles, research notes, all sorts of things, and we're ready to launch into this material and really unpack it.
Sounds good. There's a lot to cover here.
Yeah, definitely. Our mission for this deep dive is to understand this tech from the ground up. You know, how it actually works, the components, a bit about its history maybe, the challenges and limitations.
Right. What you can and can't do with it.
Exactly. And the cool new stuff that's changing the game, who the big players are, and maybe most importantly for a lot of listeners, how it stacks up against other ways you might connect online.
Absolutely. One thing that jumps out from all the sources right off the bat is its critical role.
You mean for rural areas?
Exactly. For huge numbers of people, especially out in rural, remote spots where, let's face it, fiber or cable are probably never going to reach. Satellite internet isn't just an option. It's often the only way to get decent broadband speed internet.
So let's start right there. At the most basic level, what is satellite internet?
It's broadband service, simple as that. But instead of coming through wires buried in the ground, the connection reaches you via radio signals bouncing off communication satellites orbiting Earth.
Okay, so if it's fast enough to be called broadband, we just call it satellite broadband.
Pretty much, yeah.
Yeah.
The fundamental difference is just the delivery mechanism. Radio waves through the air and space instead of light pulses in fiber or electrical signals in copper cable.
Which means you don't need any physical lines running to your specific house.
Precisely. That's the absolute key advantage. It's superpower, if you like. And it's why it's so vital for closing that digital divide we hear so much about.
Okay, so what are the main pieces that make this work?
Well, it boils down to three main components working together. First, you need the satellite itself, obviously, up in orbit.
Right.
Historically, these were mostly way out in geostationary Earth orbit, or GEO, very high up. But the big shift now, and the sources really hammer this home, is towards constellations, big groups of satellites much closer in low Earth orbit, LEO, sometimes medium Earth orbit, MEO too.
Okay, satellite up there, what else?
Second, you need ground stations. These are sometimes called gateways or Earth stations. They're the connection points on the ground that link the satellite network to the rest of the global internet, the big fiber optic backbone.
The bridge back to Earth, basically.
Exactly. And third, you have the equipment at your end, the user equipment. Typically, that's the dish you mount outside your house and a modem inside.
Okay, so if I'm sitting at home trying to load a web page, walk me through the simple path again. My request goes from my laptop to
To your modem, usually connected to your router, then to the dish outside.
dish beams it up.
Yep, up to the satellite catches it, and then relays it back down. But not to you, it relays it down to one of those ground stations.
Ah, the ground station connected to the real internet.
Right. That ground station fetches the web page data you asked for from the server where it lives, sends that data back up to the satellite.
Which then beams it down to my dish.
Exactly. Your dish catches it, passes it to the modem, modem talks to your router, router sends it to your laptop, and boom, web page loads.
And this whole complicated back and forth. The key thing, as the sources emphasize, is no need for a phone line connection, no cable TV line, no special wiring coming into the house, apart from power for the dish and modem.
Correct. Just power, that dish, the modem, and critically, a clear view of the sky. That's why it's the lifeline for places where laying cable is just too difficult or expensive. Think mountains, remote farms, islands.
Makes sense. It fills a huge gap.
Absolutely indispensable in those scenarios.
Okay, let's unpack this journey a bit more, though, because request goes up, data comes down, sounds simple, but the actual journey of, say, an email with a photo attached, that sounds incredibly complex based on the details in these sources.
Oh, it is. It's quite an intricate dance when you get down to the level of individual data packets.
So let's follow one. I hit send on an email with a picture. What happens first, right on my computer or phone?
Okay, so your device's software takes that email data, the text, the photo file, and gets it ready for network travel. It's like preparing a package. It breaks the data into smaller chunks called packets or segments.
Manageable pieces.
Right. And it adds labels, headers, with crucial info, where it's going, destination IP address, where it's from, source IP address, how the pieces should be reassembled at the other end, port numbers to make sure it gets to the right application, like your email program.
All the addressing information.
Exactly. And also checksums, which are little calculations to help detect if the data got corrupted along the way. This whole process involves protocols like TCP and IP, putting the data into the right format for the internet. Then it gets put into another envelope, like an Ethernet or Wi-Fi frame, with local addresses for your home network and sent to your router.
My home router. Okay, what's its job?
Your router is the gateway out of your local network. It takes that frame, strips off the local addressing, then it usually does something called network address translation, or NAT.
NAT, right. That's where my private home IP address gets swapped for a public one.
Precisely. Most homes have many devices, but only one public IP address assigned by the internet provider. NAT lets all your devices share that single public address. The router keeps a table, like a doorman, remembering which internal device made which request, so when the reply comes back to the single public address, it knows which laptop or phone to send it to.
And with satellite, this might be even more complicated. Carrier-grade NAT.
Yes. Often satellite providers use carrier-grade NAT or CGNAT. This means you might even be sharing that public IP address with other satellite users, not just devices in your own home. It helps conserve limited public IP addresses, but can sometimes cause issues for things like online gaming or hosting servers.
Okay, so the router handles the address swapping, then it sends the packet. Where? To the dish?
To the user terminal, yes.
Oh, okay.
Which includes the modem and the dish, often called dishy for Starlink, for instance. And this is where things get really specific to satellite communication.
This is the magic box on the roof converting my email into space signals.
Sort of, yeah. It's a highly sophisticated piece of kit. It acts as a specialized modem and a very clever antenna. First, it needs to turn the digital data, the ones and zeros from your router, into analog radio waves that can actually travel through the air and space. This process is called modulation.
Modulation, like encoding the bits onto the wave.
Exactly. It uses techniques. The sources mention QPSK or QAM, which are ways to change the radio wave's properties, its phase, its amplitude, or both, to represent those digital bits. Higher-order QAM schemes can pack more bits into each change, meaning faster speeds, but they need a cleaner, stronger signal.
Makes sense. More complex signal, easier to mess up.
Right. And space is a noisy environment, plus the signal travels a long way. How do you make sure the message gets through without errors?
Good question. Does it just resend if there's an error? That sounds slow.
That would add massive delays, especially with the long distances involved. So before modulation, they add something called forward error correction, or FEC.
Forward error correction.
Yeah, they add extra redundant bits to the data stream in a mathematically clever way. It's like adding extra clues or parity checks. The receiver at the other end of the satellite or the ground stations can use these extra bits to detect and even correct a certain number of errors that occur during transmission without needing to ask for a retransmission.
So it fixes errors on the fly. That must be crucial for reliability.
Absolutely critical for a reliable satellite link. After adding FEC, the data gets structured into specific frames suitable for satellite transmission, and then it's modulated into radio waves.
Okay, data is now radio waves with error correction built in. How does the dish aim it at the right satellite, especially those LEO ones that are zipping across the sky?
That's where the really advanced antenna technology comes in, particularly phased arrays, which systems like Starlink use, instead of a traditional dish that physically moves to track a satellite.
Which would be slow and clunky for fast-moving EOs?
Exactly. A phased array antenna has many small fixed antenna elements. By precisely controlling the timing the phase of the signal sent to each little element, it can electronically steer a focused beam of radio waves in a specific direction without any moving parts.
Beamforming.
That's the term, yes. For the uplink signal going to the satellite, DC forms a narrow beam aimed precisely at the target satellite. This maximizes the signal strength getting to the satellite and also minimizes interference with other satellites or ground systems.
And it has to keep adjusting this beam constantly.
Continuously. As the LEO satellite moves across the sky, the phased array adjusts the beam electronically to track it perfectly. It even anticipates the handover to the next satellite coming into view. This signal is sent on specific uplink frequencies, often in the Q-band, like 14.0 to 14.5 gigahertz for Starlink.
Wow. That's some serious real-time computation and control just happening in the dish on your roof.
It's truly remarkable engineering. It's what makes these LEO constellations practical for consumers.
Okay, so that focused beam carrying my email packet travels up into space. What happens when it hits the satellite?
The satellite's own antenna, often also a phased array, receives the signal. By the time it gets there, it's incredibly weak, right? Mixed in with cosmic background noise.
Needs a boost.
Definitely. First stop is a low-noise amplifier, or LNA. Its job is to amplify the very faint signal while adding as little extra noise as possible. Then, the satellite does the reverse of what your dish did. It demodulates the radio wave back into digital bits.
Gets the ones and zeros back.
Right. And then it applies the forward error correction decoding. It uses those extra bits we talked about to find and fix any errors that crept in during the journey up from Earth.
Okay, clean data packet recovered. Now, you mentioned these newer satellites aren't just mirrors in the sky, they have processing power.
Yes, this is a key difference from older bent pipe GEO satellites. Those mostly just received a signal, amplified it, maybe shifted its frequency, and sent it straight back down. Modern satellites, especially in LEO constellations like Starlink, have significant onboard processing.
What can they do?
They can actually inspect the packet. They look at the IP header, just like a router on the ground does. They read the destination IP address.
They make a routing decision in space.
Exactly. This is a game changer. Based on that destination address, the satellite's processor decides the next hop for that packet. Should it be beamed down immediately to a ground station below? Or should it be relayed to another satellite first?
Using those laser links you mentioned, intersatellite links.
Precisely. Intersatellite links, or ISLs. Many modern LEO satellites are equipped with laser communication terminals. These allow them to shoot data packets directly to neighboring satellites using highly focused laser beams.
Lasers in space. Why lasers?
Several big advantages. First, extremely high bandwidth. They can carry a ton of data. Second, they don't use radio frequency spectrum, which is crowded and requires licensing. Third, the beams are very narrow, which means they're secure and don't cause interference.
But wait, these satellites are moving incredibly fast, thousands of miles an hour, and they're far apart. How on earth do they keep a laser beam locked onto another moving satellite?
That is one of the most complex challenges. It's called pointing, acquisition, and tracking, or PTA. It requires incredibly sophisticated optical systems, stabilization, and control algorithms to find the other satellite, establish the laser link, and maintain it precisely, even with vibrations and movement. It's a huge technical feat.
I'll bet. So these ISLs create a network, a mesh network in space.
Exactly. The satellites form a mesh network, constantly talking to each other via these laser links. They run routing protocols, similar to the internet on Earth, to figure out the best path for a data packet to take through the space network. Maybe it hops across several satellites before heading down to Earth.
That sounds like it could really reduce the time it takes for data to travel long distances, right? If it doesn't have to keep going down to Earth and back up.
Absolutely. Imagine sending data from London to Tokyo. Instead of going down to a ground station in Europe, up, down, up across continents, it could potentially zip across several satellites over the pole via ISLs and only come down to a ground station near Tokyo. That could be significantly faster and lower latency than relying solely on terrestrial fiber routes for that entire path.
A true space-based backbone. Okay, but eventually my email packet needs to get to the actual email server, which is on Earth, so it has to come down, right?
Correct. At some point, whether it's relayed directly from your dish or after hopping across ISLs, the packet needs to reach a ground station. These are the crucial bridges back to the terrestrial internet.
What do these ground stations look like? Are they just bigger versions of my home dish?
Much bigger generally. They're large facilities, often called Earth stations or Earth terminal complexes. They house large, high-gain dish antennas, sometimes steerable ones to track LEO satellites, or maybe phased arrays too. The term teleport is often used specifically for these major hubs that connect satellite networks to the big terrestrial fiber networks.
Okay, so the packet arrives at the ground station's big antenna. What happens inside the facility?
Similar process to the satellite receiving, but in reverse and getting ready for the ground internet. The antenna collects the signal, it's amplified, again, LNA, demodulated back to digital bits. The FEC is decoded to fix errors, and any satellite-specific framing is removed. What you're left with is the standard IP packet containing your email data.
Just a regular internet packet again?
Yep. And the ground station acts like a big, powerful internet router at this point. It's connected, usually via massive fiber optic links, directly into the internet backbone. It reads the destination IP address on your packet.
And figures out where to send it next on the regular internet.
Exactly. It uses standard internet routing protocols like BGP, Border Gateway Protocol, to determine the best path across the terrestrial network to get that packet to the email server it's addressed to. If carrier-grade NAT is involved, the ground station might also handle the final address translation steps here before sending the packet out onto the public internet.
Wow, that is quite a journey. From my keyboard into radio waves, beamformed to space, error corrected, maybe zapped by laser to another satellite, routed down, turned back into bits, and then onto the normal internet.
It really is an astonishing chain of technologies working together seamlessly. And of course, the confirmation your email was sent or the web page data you requested follows that whole path in reverse. Internet server to ground station up to satellite, maybe across ISLs, down to your dish, modem, router, computer.
Incredible. It makes you appreciate what's happening behind the scenes when you just click send.
Definitely gives you a new perspective on hitting refresh on a web page.
Okay, if you're finding this deep dive interesting and you want more content like this where we unpack complex topics, please consider subscribing to the channel and following us. We explore something new that's intrigued us every time. All right, we've traced the packet's path. Now, how does the location of the satellite, its orbit, affect how this all actually performs for someone using it? You mentioned GEO, LEO, MERIO. It sounds like distance is a big deal.
It's arguably the single biggest factor impacting the feel of the connection, especially the responsiveness, which comes down to latency.
Let's start with the traditional approach.
Yeah.
Geostationary Earth orbit, GEO. Where are those satellites?
They orbit way, way out there,
Okay.
about 35,786 kilometers or roughly 22,236 miles, directly above the Earth's equator.
That's really far.
It is. But the key thing about that specific altitude is that a satellite there orbits the Earth at the exact same speed the Earth rotates. So from our perspective on the ground, it appears to hang motionless in the same spot in the sky.
Ah, hence geostationary. So your dish can just point at one spot and stay locked on.
Exactly. That simplifies things a lot on the ground. One satellite can also cover a very large geographic area, like a whole continent. That's why they were the standards for a long time for things like satellite TV and early internet.
Okay, sounds convenient. But the downside is that huge distance, right? What does it do to performance?
The downside is latency, massive latency. Physics dictates how fast the signal can travel the speed of light. To get from your dish up to that satellite 36,000 kilometers away takes about 120 milliseconds.
Okay.
Then the signal has to come back down to the ground station, another 36,000 kilometers or so, another 120 milliseconds. That's 240 milliseconds just for one way of the communication loop.
So for a round trip, my request going up and the data coming back down, you double that.
Roughly, yes. The absolute minimum pure physics round trip time just for the space hops is around 480 to 550 milliseconds, almost half a second. But then you have to add processing time on the satellite, on the ground stations, delays traversing the internet. In reality, the typical round-trip time or ping you experience on a GEO satellite connection is often between 600 and even 1,400 milliseconds.
Whoa. Over a second, potentially?
Easily over a second in many cases. Compare that to a decent fiber or cable connection, where your ping might be 15 to 40 milliseconds, or even old dial-up, which is maybe 150, 200 milliseconds. GEO latency is in a whole different league.
That must make certain things almost unusable. What suffers most?
Anything interactive and real-time. Online gaming, especially fast-paced shooters or racing games, forget about it. The lag makes it completely uncompetitive, often unplayable.
You'd be toast before you even saw the enemy.
Pretty much.
Yeah.
Real-time video conferencing is also painful. You get those awkward pauses and people talking over each other because of the delay. Secure websites, HTTPS, take longer to initially load because the security handshake involves multiple back-and-forth messages, each hit with that huge delay. Remote desktop access or using a VPN feels incredibly sluggish. Every click, every keystroke has that second-long round trip.
So are there ways to fix that latency on GEO?
Not the fundamental physics part. Providers use tricks like TCP acceleration, prefetching web content, special software stacks. These can help mask the latency sometimes, making web pages feel like they load a bit quicker once they start, but they don't change the speed of light. That minimum half-second round trip delay is always there.
Okay, so GEO, stable coverage, simple dish pointing, but terrible latency for anything real-time. What about the newer low Earth orbit, LEO, systems like Starlink?
LEO satellites are much, much closer to Earth. Instead of 36,000 kilometers up, they're typically orbiting between 500 and 2,000 kilometers. Starlink's constellation, for example, is around 550 kilometers altitude.
That's a massive difference, like 60 times closer.
Something like that, yeah. And that drastically shorter distance is the huge advantage of LEO. It translates directly into much, much lower latency.
How much lower are we talking?
Instead of 600 plus milliseconds, the average round-trip time for Starlink, according to the sources, is typically around 45 milliseconds. Sometimes even down into the 20s or 30s, depending on your location relative to satellites and ground stations.
45 milliseconds, that's practically like wired internet.
It's very close. Testing often shows Starlink latency being only maybe 2 to 20 milliseconds higher than terrestrial fiber or cable in the same region. It's a night and day difference compared to GEO.
So what does that mean for usability? Gaming, video calls.
It makes a world of difference. Streaming HD and 4K video is seamless. Most online gaming becomes totally viable, even many faster-paced games. Video conferencing feels natural, without those awkward delays. Secure websites load quickly. It feels much more like a modern, responsive internet connection.
Okay, LEO sounds like the clear winner for performance. What's the catch? Why didn't we just use LEO all along?
The big trade-off is complexity and coverage per satellite. Because they're so much closer, each LEO satellite only sees a much smaller patch of the Earth's surface at any given time. And they're not stationary. They're whipping around the Earth incredibly fast, completing an orbit in maybe 90 minutes or so.
So they fly over you really quickly?
Exactly. To provide continuous coverage, so you don't lose connection every few minutes as one satellite flies out of view, you need a lot of them. A whole constellation, potentially hundreds or even thousands of satellites, constantly orbiting and handing off your connection seamlessly from one satellite to the next as they pass overhead.
Managing thousands of satellites, coordinating them, handing off connections without dropping. That sounds incredibly complicated.
It is immensely complex. It requires sophisticated constellation management software, precise tracking, and that fast electronic beam steering from the phased array antennas on both the user terminals and the satellites themselves. Making sure that handover from one satellite to the next is completely seamless is a major technical challenge.
So LEO gives you low latency, but requires this huge, complex, constantly moving swarm of satellites.
That's the essence of it. You also mentioned medium Earth orbit, MEO.
Right. Where does that fit in?
MEO is, as the name suggests, in between LEO and GEO, typically orbits between 2,000 and maybe 35,000 kilometers. There's a system called O3b, for example, that operates around 8,000 kilometer altitude.
A middle ground?
Exactly. It offers a compromise. Latency is lower than GEO for O3b. It's around 125 to 150 milliseconds round trip. Better than GEO's 600 plus plot, but not as good as LEO's sub 50 meters. But because they're higher than LEO, each satellite covers more ground. So you don't need quite as many satellites for continuous coverage as a LEO constellation. O3b AMPower is their newer system in the same orbit, but with much higher throughput.
So MEO is sort of a balance between latency and constellation size complexity?
You could put it that way, yeah. It often serves specific markets like cruise ships, governments, or enterprise customers that need better than GEO latency, but maybe don't need the absolute lowest latency of LEO or can't support a LEO ground system.
So the big takeaway on performance really hinges on that orbit, doesn't it?
Yeah.
GEO means stability but high latency. LEO means low latency but high complexity and cost for the constellation itself.
That's the fundamental trade-off, and it dictates the kind of experience you're going to get as a user.
Just a reminder, if you enjoy these kinds of detailed explorations, subscribing to Silent Mind Studio and following us is the best way to catch every deep dive we do. Okay, so even with these amazing LEO systems offering much better performance, satellite internet isn't perfect. It still faces some inherent challenges and limitations, right? What are the main ones the sources point out?
Yeah, absolutely. Even LEO isn't immune to everything. Besides the GEO latency issue we hammered home, a big one that affects all satellite communication to some degree is interference, especially from weather. The term you hear most often is rain fade.
Rain fade sounds ominous. Does it mean my internet cuts out every time it drizzles?
Not usually, no. But heavy rain, snow, sleet, even very dense fog or storm clouds can definitely impact the signal. Water droplets in the atmosphere absorb and scatter radio waves, especially the higher frequencies like the Ku and Ka bands used by most modern satellite internet systems because they offer more bandwidth.
So bad weather basically weakens the signal between my dish and the satellite.
Exactly. The signal gets attenuated, meaning it loses strength. That's rain fade. Now, providers know this is going to happen, so they design their systems with what's called a rain margin.
Like extra power built in.
Sort of, yeah. It's extra link budget, extra signal strength designed into the system to overcome a certain amount of expected weather attenuation. They might also use adaptive uplink power control, where your dish temporarily transmits a stronger signal during a downpour. But a really key technology here is adaptive coding and modulation, or ACM.
ACM, right. How does that help with rain?
It's really clever. The system constantly monitors the quality of the signal path. If it detects conditions degrading, maybe because of heavy rain, it can dynamically switch on the fly to a different way of encoding the data.
Huh.
It might use a scheme that's more robust, more resistant to errors, but maybe carries slightly fewer bits per second.
So it trades a bit of speed for reliability during the storm.
Exactly. It prioritizes keeping the link stable, even if it means temporarily lowering the maximum throughput. Then, when the weather clears and the signal quality improves, ACM automatically switches back to a faster, more efficient modulation and coding scheme. It adapts to the conditions in real time.
Does the size of my dish make a difference in bad weather?
Yes, it does. A larger dish physically captures more of the incoming signal and can focus the outgoing signal more tightly. So generally, a larger dish provides a better rain margin, more resilience. However, larger dishes cost more for the consumer to buy and install, so there's a trade-off. Providers often opt for smaller, cheaper user dishes and compensate with more powerful and expensive satellites and sophisticated techniques like ACM.
Okay, so weather is a factor. What else can block or interfere with the signal?
The absolute necessity is a clear line of sight. Your dish needs an unobstructed view of the part of the sky where the satellites are. For GEO, that's a fixed spot. For EO, it's a wider area the satellites pass through.
What kind of obstructions are we talking about?
Trees are a big one. Buildings, obviously. Even dense leaves on trees in the summer can absorb and scatter the signal, especially at those higher frequencies above 2 gigahertz. When you install a dish, you really have to consider potential obstructions and even think about things like future tree growth.
So you might need to trim branches periodically.
Potentially, yeah. And there's also something called the Fresnel zone to consider.
Fresnel zone.
Yeah.
Sounds technical.
It's basically an invisible rugby ball-shaped area around the direct line-of-sight path. Even if you have a clear view directly to the satellite, objects intruding into this zone near the path, like the side of a building, a nearby tree trunk, even the ground, if the dish angle is low, can cause reflections that interfere with the main signal and degrade performance.
Huh. So it's not just a laser beam path, it needs some clear space around it too.
That's a good way to think about it, especially for optimal performance. Another major consideration, of course, is cost.
Right. We touched on this. It's generally pricier than cable or DSL.
Generally, yes. Especially when you look at the total cost. There's the upfront equipment cost, the dish, and modem. That can range from nearly free, with some promotions on older systems, to several $100s, particularly for newer tech, like Starlink initially was. Installation might be an extra fee, too, unless you do it yourself.
And the monthly bill?
Monthly service fees tend to be higher than basic cable or DSL plans. You're often looking at anywhere from $50 up to $150 or even more per month, depending on the provider, the speed tier, and the data allowance. So if you compare the cost per megabit per second, satellite often comes out higher than readily available terrestrial options.
And data caps are still a thing.
Very much so, though it's changing. HughesNet and Viasat, the main GEO providers, often advertise unlimited data. But, as the sources clarify, this usually means you don't get hit with surprise overage charges. Instead, they have priority data allowances.
Like a monthly limit?
Yeah. For HughesNet, it might be 100 or 200 gigabytes. For Viasat, maybe up to 850 gigabytes on higher plans. Once you use up that priority data in a month, your speeds get throttled, slowed down significantly, sometimes to near dial-up speeds for the rest of the billing cycle.
Ouch. So unlimited, but potentially unusable after you hit the limit.
It can feel that way, yeah.
Yeah.
Starlink's standard plan currently offers truly unlimited data with no hard caps, which is a big differentiator. However, they note that performance can still vary based on network congestion in your area, meaning speeds might slow down during peak hours if lots of users are online. They also offer priority plans for businesses or heavy users, which do have specific priority data tiers, like 40 gigabit up to multiple terabytes. And exceeding those means you get lower priority than standard users during congestion.
So even with unlimited, you need to be aware of potential throttling or slowdowns.
You definitely need to read the fine print on any plan. Finally, one limitation is just its practicality in populated areas.
You mean if you can get fiber or cable, you probably should.
Pretty much. While satellite internet works almost anywhere with a clear sky view, including cities, it's generally considered a last resort option if you have access to good wired broadband. Fiber, cable, even fast DSL or fixed wireless will typically offer better latency, especially compared to GEO, potentially higher speeds, more consistent performance, and often a lower cost. Satellite strength is reaching places those other technologies don't.
Let's circle back to the tech itself for a moment. We talked about the user terminal, the dish, and modem. Can we get a bit more specific about what's actually in there?
Sure, we can think of it as having two main parts. The outdoor unit, ODU, which is the dish and the electronics mounted on it, and the indoor unit, IDU, which is typically the modem box inside your house.
The ODU is the bit outside braving the elements.
Right, that's the parabolic dish antenna itself.
Hmm.
Getting it positioned correctly is crucial, pointing it at the right azimuth direction and elevation angle. Depending on the satellite system, you might also need to adjust polarization or skew for the best signal. And as we said, it needs that clear line of sight.
And there's usually an arm sticking out in front of the dish.
Yes, that holds the feed horn and the key radio frequency electronics. The feed horn is precisely positioned at the dish's focal point to gather the reflected signals coming down, or to illuminate the dish efficiently for signals going up. Mounted right there, you typically find two critical components.
Which are?
For the uplink, sending data to the satellite, there's the BUC, which stands for Block Up Converter. It takes the relatively low-frequency signal from the modem, IDU, converts it up to the high satellite frequency, like Ku or Kyle band, and powerfully amplifies it so it can make the long journey to space.
Okay, BUC for sending up. What about receiving?
For the downlink, receiving data from the satellite, there's the LNB, or Low Noise Block Down Converter. Its job is to capture the extremely weak signal collected by the dish, amplify it significantly while adding very little electronic noise of its own, that's the low noise part, filter out unwanted frequencies, and then convert the signal down to a lower intermediate frequency that can travel more easily over a standard coaxial cable to the indoor unit.
So the ODU handles the tricky high-frequency radio stuff and sends a more manageable signal inside.
Exactly. The IDU, the modem inside, then takes that intermediate frequency signal and does the final demodulation back into digital data. It also handles the modulation for the outgoing signal before sending it to the BUC. The IDU communicates with the satellite network to manage the connection, handles authentication, and provides the interface, usually Ethernet, to connect to your home router or computer. Standards like DOCSIS, often used for cable internet, or WiMAX have sometimes been adapted for the communication between the IDU and a satellite provider system.
Got it. ODU does RF, IDU does digital and network interface. What about the ground stations? You said they're more than just big dishes.
Oh, yeah. A ground station, or Earth Terminal Complex, is a significant facility. It's not just the antenna. The sources describe it as an assemblage of equipment and facilities. You've got the big antennas, yes, but also buildings, housing racks upon racks of sensitive receivers, powerful transmitters, modulators, demodulators, complex signal processing and decoding hardware, massive power supplies, backup systems, and high-capacity network gear to connect everything to the terrestrial internet backbone, usually via multiple high-bandwidth fiber links.
And you use the term teleport again.
Right. A teleport is essentially a major ground station hub specifically designed to interconnect satellite networks with terrestrial telecommunication networks, like the global internet or private corporate networks. It acts as that main gateway.
Do these ground stations have to follow specific rules or standards?
Absolutely. Satellite communication operates under international regulations set by bodies like the ITUR, International Telecommunication Union Radio Communications Sector, which allocates spectrum and defines technical parameters. And individual satellite operators like Intelsat or Eutelsat or SpaceX have their own specific technical requirements and standards, like IESS or ES documents, that any ground station wanting to communicate with their satellites must meet to ensure compatibility and avoid interference.
And there are networks of these ground stations.
Yes, various entities operate networks of ground stations around the world. Examples mentioned include military networks like the U.S. Space Force's Satellite Control Network, SCN, scientific networks like NASA's Deep Space Network, DSN, and commercial services like AWS Ground Station or Microsoft Azure Orbital, which offer ground station services on demand to satellite operators.
Okay, let's shift focus back up to space. What about the really advanced tech in the satellites themselves that's enabling better performance?
A huge development is high-throughput satellites, or HTS.
HTS, what makes them high throughput?
Traditional satellites often used broad beams that covered very large areas, like an entire country, with a fixed amount of total bandwidth spread across that area. HTS are different. They use advanced beamforming technology similar to the phased arrays we discussed, but on a much larger scale. They create many small, highly focused spot beams on the ground, each covering a much smaller area.
Like spotlights instead of a floodlight.
Exactly. The key is that this allows for massive frequency reuse. Frequencies used in one spot beam can be reused in other beams relatively nearby without interfering, because the beams are so focused. This multiplies the total capacity of the satellite dramatically compared to a traditional wide-beam satellite using the same amount of spectrum. Viasat 3 satellites, for instance, were designed with the goal of offering over 1 terabit per second of total capacity by using this approach.
A terabit per second from one satellite. Wow.
That's the potential HTS brings. We also already talked about adaptive coding and modulation, ACM, which is crucial satellite tech for optimizing the link based on real-time conditions.
Right, trading speed for reliability when needed.
Yep. Another aspect is multi-frequency operation. Modern systems often use multiple frequency bands, Ku-band, Ka-band, maybe even V-band or others. Each band has different characteristics. Ka-band offers more bandwidth potential, but is more susceptible to rain fade than Ku-band. Using multiple bands gives operators flexibility to manage capacity and resilience.
And those laser inter-satellite links again.
Definitely advanced tech. We covered how they create that mesh network in space, reducing reliance on ground stations for long-haul traffic and potentially lowering latency by keeping data up in space for longer parts of its journey. They're fundamental to the architecture of constellations like Starlink's newer generations.
The sources also mention that canceled Vulture project, ultra-long-duration aircraft.
Yeah, the DARPA Vulture concept. It was a satellite, but related in aiming for high-altitude connectivity. The idea was large, solar-powered, unmanned aircraft flying in the stratosphere around 20,000 meters up, acting as communication relays.
Much lower than LEO satellites.
Way lower. The theoretical advantage was extremely low latency because of the short distance, potentially as low as 0.25 milliseconds round trip to the aircraft platform itself. It was exploring a different way to get connectivity from above, but faced huge technical hurdles with power, endurance, and station keeping, and didn't proceed. But it shows the kind of thinking happening around reducing latency by minimizing distance.
Fascinating concept, though. And satellite tech isn't just for internet, right? Other scientific uses.
That's right. The underlying principles of transmitting and receiving signals via satellite are used in many fields. Oceanography uses satellites extensively to monitor sea surface temperature, height, currents, ice coverage. Seismology can use satellite data, like GPS measurements relayed via satellite, to track ground deformation related to earthquakes or volcanic activity. It's all about leveraging that vantage point in space to gather or relay data from hard-to-reach places.
As we approach the end of our deep dive, let's talk about the companies actually providing these services. Who are the main players you'd encounter if you were looking for satellite internet today, especially in the U.S.?
The landscape is definitely dynamic, but the sources highlight 3 main players currently dominating the U.S. consumer market. You've got the 2 established GEO providers, Viasat and HughesNet.
Tell me about Viasat first.
Viasat is a major player. They operate their own high-capacity GEO satellites, including some very advanced high-throughput satellites. They offer coverage across all 50 states. Their big push has been increasing speeds, with plans offering up to 150 megabits per second download in some areas. They also generally offer higher priority data caps than HughesNet, sometimes up to 850 gigabytes per month on top-tier plans before speeds are throttled.
Okay, wide coverage, high speeds for GEO, decent data caps. What about HughesNet?
HughesNet has been around a long time in satellite communications. They also use GEO satellites and cover all 50 states. Their service, HughesNet Fusion, tries to blend satellite and terrestrial wireless to improve latency for some things. Their pure satellite plans typically offer speeds up to 25 millips download. They often position themselves as a more budget-friendly option for basic connectivity, but their priority data caps are generally lower, often in the 100-200 gigabit range, after which speeds slow significantly.
So established GEO players, Viasat generally faster with more data, HughesNet maybe cheaper entry point but lower speeds and caps, and then the disruptor.
And then there's Starlink from SpaceX. They've really shaken things up with their massive low Earth orbit LEO constellation. As we discussed, the huge advantage is dramatically lower latency, typically 20-40 milliseconds, making it feel much more like terrestrial broadband. And speeds for the standard residential service typically range between 50 and 200 mbps download, though it can vary depending on location and network load. A key feature is that their standard plan offers truly unlimited data with no hard caps, though speeds can slow during peak congestion times. They're also rapidly expanding coverage globally as they launch more satellites and offer portable and mobile options for RVs, boats, etc.
So Starlink brings the low latency and unlimited data, but maybe coverage is still growing compared to the established GEO providers.
Coverage is expanding very quickly, but yes, Viasat and HughesNet have had that nationwide GEO coverage locked in for longer. Starlink is getting close to covering most populated areas, but there might still be some waiting lists or spots where service isn't available yet.
Are there other big players we should be aware of, maybe more globally?
Definitely.
Yeah.
OneWeb is another major company deploying a large EO constellation, primarily targeting enterprise, government, aviation, and maritime markets, but potentially moving into consumer markets too. And then there's Amazon's Project Kuiper.
Amazon's getting into satellite internet.
Yes, they are actively building out their own LEO constellation, with plans to launch thousands of satellites to compete directly with Starlink and OneWeb, aiming to serve underserved communities globally as well as enterprise customers. So the LEO space is getting crowded and competitive.
So if you had to summarize the quick comparison for someone choosing today in the U.S. based on the sources.
Okay, super quick summary. Speed. Starlink generally offers the highest typical speeds,
Yeah.
5,200 Mbps. Viasat next, up to 150. HughesNet lowest, up to 25. Latency. Starlink wins by a mile, LEO 2040 meters, versus Viasat and HughesNet, GEO 600 plus amps. Coverage. Viasat HughesNet have established nationwide U.S. coverage. Starlink is rapidly expanding globally but might still have gaps. Data. Starlink standard is unlimited, with congestion caveats. Viasat HughesNet use priority data caps before throttling. Pricing. HughesNet often cheapest entry. Viasat Starlink generally pricier monthly but offer better performance data. And remember, Starlink often has a higher initial equipment cost.
That's a great snapshot. And again, always check the specifics for your location and read the plan details carefully regarding costs, equipment, data, and potential throttling.
Absolutely essential.
We're nearing the end of our journey. This seems like a good time for another quick reminder. If you appreciate this level of detail, please subscribe to Silent Mind Studio and follow us for more deep dives. Okay, final big comparison. We've looked at how satellite works, the tech, the players. How does satellite internet, in its modern forms, actually stack up against the other ways people get online? Fiber, cable, DSL, 5G.
Right, the alternatives.
Yeah.
This really puts satellite's role in perspective. Let's start with the gold standard. Fiber optic internet.
Fiber. Everyone wants fiber, right?
Pretty much, if they can get it. Fiber offers the fastest speeds, easily 1 gigabit per second, or even multi-gig symmetrical, same speed up and down. Lowest latency, typically under 20 milliseconds. It's fantastic.
So satellite doesn't really compete where fiber exists?
On pure performance, no. Fiber wins hands down on speed and latency, but satellite's advantage is availability. Fiber lines have to be physically laid to your home, which is expensive and mostly limited to denser population areas. Satellite is available almost anywhere with a sky view, so satellite wins where fiber doesn't reach.
Okay. What about cable internet, using the TV lines?
Cable is the next best for many people. Widely available in cities and towns, offers high speeds, often 100 millip's up to 1 Gbps download, though upload is usually slower. Latency is pretty good, typically 20-50 milliseconds, much better than GEO satellite. Comparable or slightly higher than LEO.
Again, limited by where the cables run.
Exactly. Where cable infrastructure exists, it generally beats satellite on speed, consistency, and latency versus GEO. Where cable doesn't run, typically more rural areas, satellite becomes the option.
All right, next up, DSL, digital subscriber line, using old phone lines.
DSL is often more widely available than cable or fiber, reaching further into suburban and some rural areas. But speeds are highly variable, heavily dependent on your distance from the phone company's exchange. It can range from maybe 5 millip's up to 100 millip's if you're lucky, and close to modern equipment.
How does satellite compare to DSL?
This is where it gets interesting. Modern satellite, especially Starlink or Viasat's faster plans, often offer faster download speeds than many typical DSL connections, especially older ones or those far from the exchange. Latency-wise, DSL, around 30-50 meters, beats GEO satellite easily, but LEO satellite, 20-40 meters, is actually comparable or even slightly better than DSL latency. So satellite often wins here on speed and wins on availability where DSL isn't offered or the phone lines are too poor for decent service.
Okay, one more. 5G home internet or fixed wireless access, FWA, using cellular signals.
Right. This uses radio signals from a nearby cell tower, providing internet to a stationary receiver at your home. It's becoming more common, especially as an alternative to DSL or cable. Speeds vary a lot based on signal strength and tower congestion, maybe 50 Mbps up to several hundred MVPs in good conditions. Latency is generally low, comparable to LEO satellite or cable.
So satellite versus fixed wireless.
Modern LEO satellite like Starlink can offer comparable or sometimes even faster speeds than 5G FWA, depending on the specific location and network load. Latency is similar. The key differentiator, again, is often availability. Fixed wireless requires you to be within range of a suitable tower with capacity, and line of sight can still be an issue due to terrain or buildings. Satellite works even where towers can't reach or aren't economical to build.
So across the board, the recurring theme is Where good wired options like fiber or cable exist, they usually win on performance or cost. But where they don't, satellite, especially modern LEO satellite, becomes a very strong contender, often beating older DSL and sometimes competing well with fixed wireless, but most importantly, being available almost everywhere else.
That's the perfect summary. Satellite internet is fundamentally about bridging the gap, connecting the unconnected. It's often the only viable high-speed option for millions in remote and rural areas, despite potential drawbacks compared to terrestrial tech where those alternatives exist.
Awesome. Let's finish off by tackling some common questions or maybe myths people have about satellite internet, kind of a rapid-fire round. First up, how fast is it really?
As we saw, it varies from 25 millipedes with HughesNet up to 150 millipedes with Viasat and typically 5200 millipedes with Starlink. So definitely fast enough for most things: browsing, HD 4K streaming, emails. Not usually fiber fast, but much better than dial-up or slow DSL.
Myth 1, satellite internet is always painfully slow.
False. Modern systems offer genuine broadband speeds. GEO latency can feel slow for interactive stuff, but the download speeds themselves are often quite good now, especially with Viasat HTS and Starlink EO.
Myth 2, it completely stops working every time it rains.
False. Heavy rain or snow can cause temporary signal issues, rain fade, potentially brief outages in extreme storms. But it's usually short-lived. Providers build in margins and use tech like ACM to mitigate it. And let's be honest, severe weather can knock out wired internet too by downing lines or power.
Myth 3, this is just way too expensive for regular people.
It can be pricier than basic cable or DSL, especially upfront costs for equipment or higher tier plans. But for rural users where it's the only option, the cost is relative to having broadband versus having none. And prices are becoming more competitive, particularly as EO systems scale up.
Myth 4, you can't stream Netflix or do Zoom calls on satellite.
Definitely false. Modern speeds easily handle HD and even 4K streaming. Video conferencing works too, though, on GEO. The latency makes it feel laggy and awkward. On LEO systems like Starlink, video calls work much better due to the low latency. The main thing to watch for streaming or calling is just your data cap, if your plan has one.
Fantastic. We have covered a ton of ground today, or maybe I should say a ton of orbit, from the journey of a single data packet leaving your device, up through phased arrays and potentially laser links in space, down to ground stations, across the internet, and back again.
It really is an incredible system when you break it down, involving so many layers of complex technology working in concert.
And the key takeaways seem clear. Satellite internet is absolutely vital for bridging that digital divide, bringing connectivity to places ignored by traditional infrastructure. And these new advancements, especially ELO constellations like Starlink, along with tech like ISLs and ACM, are genuinely revolutionizing performance, slashing latency, and boosting speeds compared to the older GEO systems.
That's right. Challenges definitely remain. Cost is still a factor, weather sensitivity is real, and GEO latency isn't going away. But overall, it's a technology that's evolving incredibly quickly and becoming increasingly capable, opening up the online world to more people than ever before.
It really leaves you thinking about the bigger picture. How might these ongoing improvements in space-based internet fundamentally reshape our idea of connected versus unconnected regions? Could we see completely new applications emerge that thrive far from terrestrial networks? Thinking bigger, what are the opportunities or even the challenges presented by having a truly global, high-speed internet backbone floating above us in space?
That's the provocative thought for the future, isn't it? It touches on everything from equitable access and economic development to space traffic management, orbital debris, and the very architecture of global communication. Definitely something to keep watching.
Absolutely. Well, that brings us to the end of this deep dive. Thanks for joining us.